That's good. It looks like you might have lost a carbon here, or it's drawn so condensed that it's hard to see that there's 2 carbons here. Or no, am I confused? You took off. Oh, no, it's right there. You're doing fine. Yeah, you're right. And you worked out that that's a ketal. Good. How do we know this is a ketal and not an acetal?
The 2 R groups.
That's right. We have 2 R groups because we started with a ketone and not an aldehyde. And you also correctly marked that this was the hemiketal because we were only halfway through and the carbonyl oxygen was still around. What ultimately happened to the carbonyl oxygen? The carbonyl, did you draw where that went? You might have. So you showed the carbonyl, you showed that leaving. It's good to actually show that that leaves as water. So here's the carbonyl oxygen that left as water.
What at what point do we add the plus? So you put plus H2O down there. So after it leaves.
So here's where the water leaves.
Uh-huh.
This is the step where the water leaves. And so then these are supposed to be the product. So I wrote the water here because this is the product of the step where the water leaves.
Okay, yeah.
The board is getting a little bit messy, but this was the step where the water left. So after the next arrow is where I drew the water.
Okay.
You might also redraw the water here just to remind ourselves that that's one of the interesting final products. So that's one of the interesting final products that we got, even though it was produced back in this step over here. Again, we can see this is hidden carbon with 2 bonds to oxygens. Good. Well, I think that's a pretty complicated reaction, but you zipped right through that, so that was great.
So I have a question. So for our carbonyl, we have it as 2 R groups. So do we count like those 3 carbons as 1 R group and then 3 carbons off to the other side as the other R group?
That's right. All we really care about is the things that are directly connected to the carbonyl carbon. Mm-hmm. So this carbonyl carbon is connected to a carbon on the left, mm-hmm. and it's connected to a carbon on the right. Mm-hmm. That means this is a ketone, and that means it's going to produce a hemiketal and a full ketal. Mm-hmm. If this was connected to a carbon on one side and a hydrogen on the other side, then it would be an aldehyde. And then we would produce a hemiacetal and a hemiketal. So it's completely irrelevant that the 2 carbons happen to be connected through the back door over here. All that matters is that we started with a ketone because there was a carbon on both sides. So one thing to point out here is that it looks like he decided not to do that proton transfer step.
Right.
And that was perfectly okay because otherwise we couldn't have seen the hemiketal. So what you had is you had the sulfate take this proton and then give the proton to the oxygen. If you had wanted to, you could have shown that happening in one step. You could have shown this oxygen taking the proton from this oxygen, and then you would have skipped this picture and gone straight to here. Either of those is fine. Either of those is fine. Actually, in the answer key, you'll usually see them skip this. But actually, this is good for us to do at the beginning because it shows the hemiketal version over here.
I was just going to look at these really quickly. Sometimes if he uses a different reagent in lecture, I get like really confused when I see it, and I don't even know where this begins. Is this that same thing? Yeah. So it's the same thing I use actually. What's the
pH?
Mm-hmm.
Now pH, remember, is just shorthand for a benzene ring. It doesn't really change the reaction at all. It just means that there's a benzene attached to the carbonyl.
Okay.
It wouldn't change the reaction at all. It just means that there's a benzene on one side of the carbonyl carbon.
Okay. And there's a special note right here. Can't make acetals or ketals under base catalyzed conditions.
That's right. After all, notice we've been doing this under acid conditions,
Mm-hmm.
right? And if you look at the handout, it says acid conditions. So this reaction would not have worked under basic conditions.
Okay.
So in a way, that's good. So we don't have to learn the base catalyzed way to make acetals and ketals.
Okay.
We only have to go over the acid catalyzed. Now, there is something you can do with alcohols and base catalysts, but that's less important, and that's not what a top priority is, so we'll have to skip that.
Okay.
The important reaction is alcohols in acidic conditions.
Mm-hmm.
Now remember that this is all reversible, which means that if you start with either of these, you should be able to make it back into a carbonyl. So let's ask ourselves, how could we make this back into a carbonyl? Well, in order to make this back into the carbonyl, how can we make this back into the carbonyl? The way to make this back into the carbonyl, well, we'd have to get the carbonyl oxygen back on, right? Mm-hmm. Notice that neither of these are the carbonyl oxygen. These are the oxygens that came from the alcohols. So if we want to reverse this, we have to put the carbonyl oxygen back on. Well, when the carbonyl oxygen left, what molecule did it leave in?
Water.
So how can we put it back on? By adding water. If we add water, that can bring carbonyl oxygens back in. Since the carbonyl oxygen left as water, if we want to put the carbonyl oxygen back on, it's kind of logical that we should add it in a water molecule. We'll go through that mechanism maybe in a minute or two. But the basic idea is that by adding water, we should reverse this. Now this whole thing is acid catalyzed. So the way to reverse this then would be to add water plus acid. Water plus acid, we need the acid as a catalyst, and then the water would bring back that carbonyl oxygen. And then that would ultimately kick these two oxygens all the way off. And we would just reverse all these steps and get back to here. That's a complicated mechanism, so we can go through it step by step in a second. But the basic idea is, in the forward reaction, the carbonyl oxygen left in a water molecule. So the way to put it back in is to add an extra water molecule to put the oxygen back on. So the point is, the way to reverse this reaction is water plus acid. And then what would be the products of that? Well, that would put the carbonyl oxygen back on, and that would kick off the two alcohols. So then that would just take us back to here. The product of adding the water plus acid would get us back to this species and these alcohols. That's why this is called a hidden carbonyl again, because it can easily be turned into a carbonyl. By the way, a good abbreviation for water plus acid is H3O+. H3O+ just means water plus acid. H3O+ just means water and acid. So this is the way this usually would be written. It would be written as H3O+. That would have the acid as the catalyst and the water to bring back in the carbonyl oxygen.
So we would just put that and then the arrow with the H3O+ and then draw our...
Then we would do the mechanism in reverse.
Okay.
That's right. We'll get to that in a moment.